Here is the very last section of our review. Hey, I said minimize. Thank you. Okay, solving equations. And you have to identify whether it's an exponential or a logarithmic an equation, because that changes your strategy. This is exponential. 32 to some power equals 4 to some power. And with the exponential ones, your challenge is to get the same base on both sides. 32 is 2 to the 5th. And that's all to the x minus 1 power is equal to 4, which is 2 squared. And all of that is to the x plus 5 power. And then I have 2 to the 5 to the x minus 1. We multiply the 5 through, so that's 2 to the 5x minus 5 is equal to, here it's 2 to the 2x plus 10. You multiply those exponents. And then once you have the same base on both sides, you set the exponents equal to each other. So now I turn this into the equation. 5x minus 5 is equal to 2x plus 10. I will move the 2x over, subtract 2x from both sides, add 5 to both sides, and you get x is equal to 5, and there's your answer. Notice in the directions I did say to check for extraneous solutions. That applies to log equations. For log equations. If it's an exponential, you don't have to worry about your solutions not working. However, it's not a bad idea to check your answer just to make sure it works, that you didn't make some kind of arithmetic error. But if all of your algebra is correct up to this point, then your answer will be correct for an exponential. So let's move on. Number 28, we have 12 and 144 as our bases. 12 is not a number to a power, like you could write it as 3 times 4 or 2 times 6. But when you're trying to change the base, you're looking for like 3 squared or something like that. The way I changed 32 to 2 to the 5th and 4 to 2 squared. So 12 won't break down, but 144, hopefully, you know that 144 is 12 squared. And that's good because my other side has a base of 12. 2x plus 7 equals, and the one on the left side is just going to hang as it is. Hang. It's hanging out over there. So I get 12 to the 3x plus 11. Left side doesn't change. Right side, I'll distribute that 2 through. That's going to be 4x plus 14. And then once you have the same base on both sides, you set the exponents equal to each other. And solve the equation. I'm going to move my x's to the left or right side. So 4 minus 3x is 1x. And I'll subtract 14. You get x equals negative 3. And there you go. Let's try this one. I see 9/16 and 3/4. Now, y'all are looking at that and you're freaking out because they're fractions, but that's because you're a wimp. Well, maybe not that, but don't let it scare you. 9/16, those are some nice numbers. 9 is really nice because 9 is 3 squared. 16 is really nice because 16 is 4 squared. And you see that right there, I now have my left side in terms of 3 over 4, which is what my right side is. So I'm happy with that. So let's flush this out a little bit more. Um, 3 over 4, or 3 squared over 4 squared is the same thing as 3/4 squared. And then all of that is still to the 3x minus 2 power. My left side is 3 over 4, all to the 5x plus 4. It's a stupid looking 5. There. Then I'll distribute. So my left side, I'll multiply that exponent through. 2 times 3x minus 2 is 6x minus 4 is equal to 3/4 times 5x plus 4. And then once I have the same bases, I have 3/4 to a power equals 3/4 to a power. I set the exponents equal, so 6x minus 4 is equal to 5x plus 4. And solve that equation, you get x equals 8. There we go. Let's see, moving on. Okay, number 30. Again, you want to try to get the same base. It's an exponential equation. The problem is 5 and 17 do not have a common base. So when you don't have a common base, what we're going to have to do is take the natural log of both sides. So I'll do the ln of both sides of the equation. And the reason I do that is because I'm going to take advantage of the property of logs that says ln of x to any power is the same thing as a times the ln of x. That's the property that we're going to use here. So when I take the ln over here, it allows me to take this exponent on the 5 and pull it down front. So now I have x times the ln of 5 is equal to the ln of 17. And then if I want to solve for x, it's x times the ln of 5. I will simply divide by ln 5, divide by ln 5, and that gives me an answer x equals ln of 17 over ln of 5. And you do not have to punch that in the calculator. As a matter of fact, I would rather you didn't punch that in the calculator. Just leave it as ln 17 over ln 5, and I'm happy with that answer. Okay, so number 31, same problem. 3 and 10 do not have a common base, so I'm going to take the natural log of both sides of the equation. That allows me to pull this exponent of x plus 2 down to the front. And watch your parentheses, because it is all of x plus 2 times the natural log of 3 is equal to the natural log of 10. And then we actually do need to distribute. The ln 3 will multiply through this equation. We have x times ln 3 and 2 times ln 3. And you can't clean that up. X times ln 3 is simply x ln 3. 2 times ln 3 is simply 2 ln 3. Equals the ln of 10. And then I need to solve for x. Now remember, your natural logs, ln 3, ln 3, and ln 10, those are just numbers. You treat those the same way as you would if there wasn't the log there. What if it was x times 3 plus 2 times 3 equals 10? Well, to solve for x, you would start by moving over everything that doesn't have an x. So I'm going to start by subtracting the 2 ln 3 from both sides of the equation. And don't try to clean that up, because it doesn't clean up nice. These cancel. 2 ln 3 minus 2 ln 3 is 0, so those cancel. I'm left with x ln 3 on the left side equals, and ln 10 minus 2 ln 3 does not combine. You cannot combine them if the logs have different numbers inside. So that's what we have. And then finally, to solve for x, it's x times the ln of 3. We're simply going to divide by the ln of 3. The ln 3's cancel, and this is what x equals. So my final answer is x equals the ln of 10 minus 2 ln of 3 over the ln of 3. Ugly answer, but that's what it is. You just don't be tempted to try to punch that in the calculator. First, because you will make a mistake. I can almost guarantee it, and you'll get the wrong answer. And second, I don't even want the decimal. I prefer these answers. So leave it like this. 32, same problem again. You cannot get a common base for 2 and 7, so I'll do the natural log, and that allows me to bring down the exponents. So I have 2x plus 4 times the natural log of 2 is equal to x times the natural log of 7. And just like that last problem, we're going to distribute the ln 2 through here. So ln 2 times both of those, which will give me 2x ln of 2 plus 4 ln of 2 is equal to x ln of 7. And now we have to try to solve for x. I've done the distributing. And to solve for x, notice my x's are on different sides of the equation. When you are solving an equation, any term that has x in it, you've got to get those on the same side of the equation. Right now they are separated, so I'm going to do, what I'm going to do to get these together is I'm going to take the one on the left side and move it over. And the reason I'm moving this one over is because my x over here, it'll leave the 4 ln 2 by itself. You could move the x ln 7 over, but then you'll have to move some other things to the right side. So I'm going to move this over. So I'm going to subtract 2x ln 2, subtract 2x ln 2, and they don't combine. So it's 4 ln 2, because over here, 2x ln 2 minus 2x ln 2 is 0. Those cancel. So I have 4 ln 2 is equal to, and do not try to combine these. It's x ln of 7 minus 2x ln of 2. You're good? You're good? Good. And I like to put my log stuff in parentheses, so there we go. Then on the right side, what we're going to do is factor the x out of both of those terms. I have x times something minus 2 times x times something, so I'm left with I pull out the x, the ln 7 minus, I pull out the x, 2 ln 2. Right side doesn't change. And then finally, I can solve by dividing, since it's x times all of that stuff, I'm going to divide by all of that stuff. Divide both sides by all that stuff. ln 7 minus 2 ln 2. And here they cancel. That cancels that. And my final answer is simply x equals all of this stuff. 4 times the natural log of 2 over natural log 7 minus 2 natural log 2. There we go. Ugly problem. That is, in my opinion, the toughest question that can be asked on the test. They're just a pain. They're just a big royal pain in the rear end. Let's see. So now on to log equations. These are not exponential anymore. This is log. And you have a couple of strategies for log equations. One of them is, this one sets up really nicely because if you have log 9 of something equals log 9 of something, if you just have log equals log and the bases are the same, then you can drop logs, drop in logs, and ignore the logs and just set the inside equal to each other. So x squared minus 3 is equal to 22. Anytime I have an exponent higher than 1, I am a fan of solving by factoring. So I'm going to subtract 22. And you get x squared minus 25 equals 0. And that factors x plus 5, x minus 5. And you get x equals negative 5, and x equals positive 5. Now, some of y'all may have been thinking, well, I don't want to factor. I hate factoring. So here's what you're thinking. X squared minus 3 equals 22. I don't know what that 3 is doing there. 22. You'll add 3 to both sides. You get x equals 25. And this technique, this strategy will work, but the problem is about half of you are going to take the square root of both sides, and you're going to say x equals 5. You've lost the negative 5 answer. So remember, if you want to solve by taking the square root, anytime the square root is your creation, it's not part of the original problem. You have to remember it's plus or minus 5. I like to factor because if you factor, then the plus and minus 5 are staring you with the two factors. Now, it is a log equation. It was originally a log equation. I canceled the logs, but the original problem had logs, which means I need to make sure that my answers both work. Even though my math was good, sometimes you have to throw one out. So if I plug in negative 5 squared is 25, minus 3, that's a positive number, so that one's okay. It doesn't matter that x is negative, it's what happens after you plug it in. And negative 5 squared does turn positive, minus 3 remains positive. If I plug in positive 5, 25 minus 3 is still positive. So both of these answers work. You don't throw them out. So we have those two strategies to solve that one. What about this one? What about this one? I have log 5 equals log 5 minus log 5. The biggest mistake people will make here is they'll drop their logs from the beginning. You don't want to get too happy dropping logs, okay? Because you can't drop logs until you have one log on each side of the equation. So what we have to do is condense this side into one single log. So I'm going to write my right side as log base 5. And since I'm subtracting logs, that can be written as x plus 6 all over 4. And my right side, I only have one log over there anyway, so I'm not going to bother changing it. Now I have log 5 equals log 5. I can drop my logs. Do not drop logs until you only have one log on both sides. So x equals x plus 6 all over 4, and we have to solve this equation. I hate fractions, so I'm going to multiply to get rid of that fraction. Multiply by 4. Over here they cancel. 4x equals x plus 6. Subtract 3, or subtract x, you get 3x equals 6, and x equals 2. And I think that'll work, but we just have to plug in to make sure we don't get anything goofy. Log base 5 of 2, that's a positive number. You cannot have negatives inside, so far I'm okay. 2 plus 6 is 8. Log base 5 of 8, that's okay. I don't get any negatives when I plug in my answer, so I'm okay with x equals 2. Okay, what about this one? Natural log plus natural log equals natural log. I'm going to condense my logs. So over here, remember you can't drop logs until you have just one log. So that's going to be x times x plus 7 is equal to ln of 18. And now I have ln of something equals ln of something. I can drop my logs. Woohoo! I need to put sound effects in here for dropping logs. And we get x times x plus 7 equals 18. And we need to solve this. I'll distribute my x. X squared plus 7x equals 18. I have an exponent higher than 1. I'm going to have to solve this by factoring. So move that 18 over. That factors to x plus 9. X minus 2. And you get x equals negative 9. And x equals positive 2. Now we just have to make sure that those work. And you always test in the original problem. You don't plug in to anything that you changed. So I plug in negative 9. If I plug in negative 9, I get log of negative 9, and negative 9 plus 7 is negative 2. That's a log of a negative number. Even though my work was good, I have to throw out negative 9 because I cannot take the log of a negative number. So now I'm going to try 2 and see if that works. ln of 2, that's okay, that's positive. And 2 plus 7 is 9, that's a positive number. So I will keep 2. Good, good? All right, let's see, let's try this one. Log 2 of x. That's this one. Notice everything does not have a log. That makes this different than the other problem. This 3 is just the 3. There's nothing else in there with it. So what we're going to have to do for this problem is we're going to actually need to move my logs to the same side of the equation. So I'm going to subtract log 2 of x. Subtract log 2 of x. Now these don't combine. You're just going to have to write them as log base 2 of 2x minus 6 minus log base 2 of x is equal to 3. I left the 3 on the right side of the equation. I subtracted the log base 2 of x, so those canceled. Now if I have log equals a number, what I'm going to do is condense these two into log base 2. If you're subtracting, that's 2x minus 6 divided by x equals 3. And then to solve this equation, we're going to take it out of log form. This is what I was doing at the very beginning of this review a long time ago. So I'm going to write this as 2 to the third power is equal to 2x minus 6 all over x. And now I'm going to solve this with algebra. 2 cubed is 8. I will multiply by x to get rid of that denominator. So over here they cancel, leaving me with 8x equals 2x minus 6. Then I'll keep working down. I'll subtract the 2x. So 6x equals negative 6. I get x equals negative 1. Now a negative number kind of makes me worried here because you cannot take logs of a negative. So let's see if I can plug negative 1 in for x. Let's see. 2 times negative 1 is negative 2 minus 6. That's negative 8. Also, log base 2 of, if I plug in negative 1 for x, I have log of a negative number. So even though my work was good and I got x equals negative 1, we actually throw that out. And since there's no other solution, that means this problem actually has no solution. There is no solution to this problem. That's frustrating. You work so hard to find out that there's no solution. All right, let's see, what else do we have? How long is this one taking? Yeah, I knew this one was going to be the longest part. Okay, same type thing. I have log equals 3 plus log something. We're going to move the logs to the same side of the equation. If you ever have a number sitting by itself without a log, this is going to be our strategy. So subtract log of x minus 3. And you get log of x minus 10 minus log of x minus 3. Over here, those canceled equals 3. I want to condense these two logs into a single log. So that's going to be log of x minus 10 over x minus 3 is equal to 3. And here we're going to take this out of log form. So if you have a log without a base written, ooh, there's a hidden base here. This problem was kind of nice because it was just a base of 2 and you could see it. This one, if there's no base written on a log, it is an understood base of 10. So I'll take this out of log form, write it as exponential. And 10 cubed is 1,000, so I have 1,000 is equal to x minus 10 over x minus 3. I will multiply both sides by x minus 3. Multiply this side by x minus 3. And that gives me, let's see, 1,000x minus 3,000. Over here, the x minus 3's cancel. Equals x minus 10. We'll subtract the x. That'll give me 999x. We'll add 3,000, gives me 3,010. And then we will divide by 999. And you get x equals 3,010 divided by 999. And 3,000 divided by 999, that's pretty darn tootin' close to 3. It's really close to 3. And the reason I want to know what that's close to is because I want to know if I plug in 3 for x or something really close to 3, if I get a negative in the original problem. So I'm going to go back in and test this. If I plug in 3, let's see, 3 minus 10. Geez, are you kidding me? 3 minus 10 is negative 7, right? So again, even though I worked it out correctly, where did I get these problems? Even though I worked this problem out correctly, when I plug in something close to 3, and you know, negative 7 isn't even close to being positive. So I don't have to worry about plugging in the exact answer. When I plug in 3, I get a negative. So again, we throw this out, and there's no solution. Yeah? All right, 2 more problems. Okay, this one. This is that problem that's it's a quadratic form, which means this is a hidden problem, that's going to end up working a lot like x squared plus 6x plus 5 equals 0, where you want to solve by factoring. What I'm going to do first is I'm going to change e to the 2x. I'm going to change that to e to the x all squared. And I have minus 2 times e to the x minus 15 equals 0. And now it's starting to take shape a lot like this problem. I see something squared minus 2 something minus 15. And what I like to do is a little substitution where I take out the e to the x and I plug a in its place. This is just temporary. We're going to come back and deal with x later, but for now, I'm going to plug in a everywhere I see an e to the x. And now it really looks like Algebra 1. A squared minus 2a minus 15. That factors to a minus 5, a plus 3. And when I solve for a, I get a is equal to 5, and a is equal to negative 3. But I didn't want to solve for a, I want to solve for x. So now we go back and plug e to the x back in for a, and we have e to the x equals 5, and e to the x equals negative 3. And then to solve this equation, we will take the natural log of both sides. So I'll do the ln, and so ln of e to the x is just x. That's one of the properties of logs. ln of e to the x is x, equals the ln of 5. And there's one answer. And then if I take the ln of this one, ln of e to the x equals ln of negative 3. That's x equals ln of negative 3. But remember, you cannot take the log of a negative number. So we throw that one out, and our answer is x equals the ln of 5. Okay, then we have one more problem. This one is going to be the same kind of problem, except now it's 3 to the 2x instead of e to the 2x. But I'm going to change 3 to the 2x to 3 to the x squared, and everything else is going to stay the same. Plus 5 times 3 to the x minus 12 equals 0. Then I'll do my substitution. I'm going to take out 3 to the x, and I'm going to plug a in its place, just to make the problem a little less intimidating. So I have 2 times a squared plus 15 times a minus 12 is equal to 0. And now we want to try to factor this. Let's see. What I'm going to do to make sure this is going to factor is... Oh, that's a 5, not a 15. Okay, thank you. So that's 5a. Sorry, I was stumbling there. But just to make sure it factors, I use this little trick that a lot of Algebra 2 teachers will teach you. 2 times negative 12 is negative 24. And I'm going to look for factors of negative 24 that add up to 5. And I can do that with an 8 and a negative 3. So since I was able to find numbers that add up to 5, that at least tells me that this will factor. We're not going to have to use quadratic form. Now, I'm going to quit with that technique here. Some teachers like to do like a plus 8 and a minus 3, and then you divide by something crazy. And I can't stand those techniques. So I'm going to go into guess and check mode, where I know I have something times something. And my first two terms have to multiply to give me 2a squared. Well, the only way you get a 2a squared is by multiplying 2a and a. And then I need factors of negative 12 to go in these spots. So numbers that multiply to give me 12 would be something like 2 and 6, right? Right? And then we just check. So 2 times 6 is 12a, 2 times a is 2a, and I am not going to get a 5 out of that. Now what I will do is I'm looking back up here. Let's see, I need an 8 and a negative 3 to give me my negative 24. Let's try negative 3 times a, and negative 3 times a positive 4 is 12. And the reason I chose negative 3 and 4 is because negative 3 times a is negative 3a, and I knew I needed a negative 3 to get this to work. And then 2a times 4 is a positive 8a, and those two do add up to 5a. So this is how this problem factors. And the beauty of factoring, y'all, is you can always check it by multiplying it out. So then when I finish solving, I get a is equal to 3 halves. We'll add 3 and divide by 2. A is equal to negative 4. And I'm not solving for a, we want to solve for x. So now I'll plug 3 to the x back in. 3 to the x equals negative 4. And we'll solve this by taking the natural log of both sides. So let's take the ln. That gives me x times the ln of 3. I can pull that x down. It's equal to the ln of 3 halves. And then I'll divide by ln 3. So x equals ln of 3 halves, all divided by natural log of 3. And there's one answer. This one, if I take the ln of both sides, ln of 3 to the x equals ln of negative 4. And you cannot take the natural log of a negative number, so I'll automatically note this one will not work. The only answer is ln 3 halves over ln 3. And I think that's it.